so like I said before, everything that we're doing, this unit is doing with a right triangle. Part of trig is knowing all of the different sides of your triangle. So sometimes you'll only have two sides and you're going to be looking for that third side. If you know two sides of a right triangle and you're trying to find a third, what would you use? Yeah, we're going to try the Pythagorean theorem. Hold on. That's supposed to go right here, by the way. Pythagorean theorem, which says what? We did that on that pink as a review, right? Pythagorean theorem says a squared plus b squared equals c squared. Just like right here, the a and the b has to be the legs of the triangle. The c is always the hypotenuse. So the c is the one that matters. It's the longest side, right? The other two don't really matter. So if I were trying to set up part A, how would I do it? What squared plus what squared? Okay, let me ask you a different question. Which one is your C? 9. So we would say x squared plus 5 squared equals 9 squared. And I apologize, there's like 0 room to write. Keep going and keep that equal sign kind of going down. So x squared plus 25 equals 81. What next? There's that 25. So x squared equals 56. How do I cancel a squared? Take the square root. Now from our first unit together, we learned how to simplify a square root. Anytime you can simplify a square root or a radical, I want you to. Which means, off to the side, we just have to see what goes into 56 and see if it breaks down. What times what into 56? 7 times 8? 8 is 4 and 2, and then 2 and 2. So how do I finish this off? I've got a group of 2's. I've got a loner and a loner. How do I work this out? What goes in, what goes out? Yeah, the groups go out. So x equals, I've got a group of 2's, right? And then I have a loner 2 and a loner 7. How do I write that inside? We multiply it. Good, let's try part B. On part B, which one is your C? The square root of 197, good. So you've got x squared plus 8 squared. How do I write this? The square root of 197 squared? And what's going to happen there? It's just going to be 197 because the square root and the squared will cancel. So if I simplify this, it'll just say x squared plus 54. Again, a square root, the squared cancel, we're left with 197. Subtract the 64. And we get 133. Then what? Square root it. 133. If you're not sure if it's prime, what could you do? Google it. Is that alright? That's what I do. I'm pretty sure it's prime. Usually I'll take a calculator if I don't have the internet with me. And I'll just divide 2 now, divide 3 now, divide 5 now. Keep dividing by prime numbers, 7, 11, 13. Once I get to about 11, 13, if still nothing's going inside, then I'll say that it's prime. I may be wrong, but... Hey, part C. How do I work this one out? Try it on your own, part C. A squared plus b squared equals c squared. pause this first.
All right, we're about to work on questions from the homework packet, so if you're watching on video, pause and work on homework, or just keep watching. Let's jump back to our notes. We're going to skip around a little bit. I do want to fill out this trigonometry section right here. Before I do that, let's jump to the next section, which is rationalizing the denominator. So if you'll get to kind of the middle of page 2 of your notes, and hit back to notes. All right, here's a little history lesson. A long time ago, this stuff was discovered, created, invented, thought up. I don't know what the right word is, but it was discovered a long time ago, before there were people living in America. Everything was over in Europe. And let's see. The king was very involved in the decision making with regards to mathematics. I think it's probably because, like, the idea of zero wasn't really ever talked about because, I don't know, to us it seems kind of silly, but zero was an idea that they didn't understand. And so if you were to talk about things like zero, I'm assuming, the king thought those kind of progressive ideas were going to risk his position. And so they made laws of things that you could and you could not talk about. I guess we'll talk about that more when we get to, well, I guess Pythagorean theorems, but the idea of square root, it was not okay to have a square root in the denominator. And this is why. What is the square root of 3? Will you get it on your calculator, square root 3? And it keeps going, right? Now, if we were going to, like, jump back to the 3rd grade and do this long division, this 1.7320508080 would go on the outside of the little division thing, and the 1 would go inside the division thing. Is that going to be an easy or a hard division problem? Like, immensely hard division problem, right? This is something, now they don't have these fancy, shiny, color-coded calculators because it's forever ago, long time ago. So they made the rule that you can't have a square root in the bottom. Now, what if I were to change this? I told you that these were the exact same number. I told you that. Now, which one's going to be easier? Is this one a little bit more doable by hand? Yeah. If you were to go back to the 3rd grade, this is how you would solve this problem. You would bring your decimal up. You would say 3 goes into 17 5 times, because 5 times 3 is 15. Subtract, you get a 2. Bring down to 3. 3 goes into 23 7 times. You kind of remember this? I mean, not probably good memories, but are you all right with this? And yeah, you would keep going, but is this doable? Yes. Is this doable? No, not really. So a long time ago, the rule came that you can't have a square root in the denominator. So the next thing I want to teach you is how to get rid of the square root in the denominator, and that's called rationalizing the denominator. So anytime we find a radical, every time we find a radical or a root in the denominator, we need to rationalize the fraction. So rationalize the denominator just means I need to get the square root out of the denominator. That's all it means. Now, I can multiply any number by 1, it stays the same, right? If I multiplied 15 by 1, what's my answer? 15. If I multiplied 8 by 1, 8. So I can multiply anything by 1, and the value of what I'm multiplying will stay the same. Now, if I pick very strategically what that 1 looks like, I could get rid of the denominator, but not lose the value of the square root of 5 over the square root of 3. Now, once we do this, our answer isn't going to look more simple. So I'm not like simplifying anything. I'm just getting the denominator so it doesn't have a square root. So what do you think? How could I get rid of that square root 3? Go ahead. Could we square it? Okay. Could we square, don't write this down. Could we square the top and square the bottom? No, we can't. Yes, that would get rid of the square root, but when I square the top and square the bottom, that's changing the value of my fraction because I'm not multiplying by 1. Does that make sense? So, good idea. But the whole point here was I wanted to get rid of that radical by squaring it. Any other ideas? Now, squaring it would work because, well, squaring it gets rid of the square root on bottom. And the reason why is this is like square root of 3 squared, right? Yeah? And that is the square root of 9, which is 3. So I can't square it, but what can I multiply by? I can't square it, but could I use kind of that same idea and multiply the top and the bottom by the square root of 3? Is that all right? Because what's going to happen here? On top, if you both have a radical, you can multiply the number inside the radical together, and it would be the square root of 15. And on the bottom, you would have what? The square root of 9, which is 3. Ta-da! Magic, yes? No, good question. You're saying longhand like we did at the beginning? No. No, that was just an explanation of why we do it this way. We've kind of evolved, so unless the instructions tell you to rationalize the denominator, you don't have to. So like when we take the SAGE test at the end of the year, you could leave an answer like this, unless they tell you to rationalize the denominator. But that was just why we do it, or why the rule was decided. Okay, let's move on to the next one. Let's skip it. Let's jump to part C. What would I have to multiply the top and the bottom by on part C in order to get that square root 10 to go away? The square root 10. I don't care about the square root on top. That's fine. It's the square root on bottom that I can't have. Now when I simplify this, on top, they both have a radical, so it's going to be the square root of 50. On bottom, 10. Now really quick, this is a 50, this is a 10. Can I simplify them and call it the square root of 5 or something? No, because one has a radical and one does not, so you can't do it that way. But what you do need to do is decide if this guy right here, if he can break down. So let's do the factor tree on the 50 to see if we have any groups. 50 is, and then 5. 5 and 10. So does it break down? I've got a group of 5, a loner 2, so let's rewrite that. Where do we write it? 5 square root 2, group goes out, loner stays in. And what's that going to be over? 10. Anything else we can do to simplify that? Now, if one has a radical, one does not, you can't simplify it. But if two numbers don't have radicals, could we? Could we simplify the 5 and the 10 right here? Yes. What goes into both 5 and 10? 5. So let's divide this by 5, and we get what? 1. Divide this by 5, we get 2, which means my final answer is the square root of 2 over 2. Part B is kind of a bugger of a problem. Would you mind if we flip over to your homework and do a couple problems from there instead? Sorry, I'm in the way. Because I want to show you a little bit of a shortcut that we could have taken right here to make it slightly faster.
Okay, let's do number 9, which says 2 over square root of 6. Let's do number 15, 4 square root of 2 over 7. Okay, trying to do these two really quick. A number 9, what would you have to multiply? Actually, a 9. A number 9, you try it. See if you can get it. Get as far as you can on number 9. The 1, what would you multiply the top and the bottom by? To get rid of this square root on the bottom. Do that. See if anything cancels. Okay, on number 9, what do you multiply the top and the bottom by? On bottom, what's left? It's like saying the square root of 36, which is just 6. What do you do on top? Yeah, do we multiply them together and get the square root of 12, or do we just kind of like set them next to each other? Yeah, just kind of mush them together. Because this does not have a radical, this does 2 square root 6. That's almost all that you can do. What do you notice about those though? Is there anything that can cancel? The 2 and the 6, right? They're both even. So I'll divide this by 2 and I'll get a 1. Divide this by 2 and get 3. My final answer is the square root of 6 over 3. Can we simplify that again and call it the square root of 2? Guaranteed somebody will try it. Can we do it? No, not that one. Good. All right, for number 15, I can do exactly what we just did. But before I start, I've noticed that the 2 and the 10 have something in common, right? They're both even. Now, because they have something in common, if I were to multiply the top and the bottom by the square root of 10, in the end, I'm going to have to break down a radical. It's easier to reduce at the beginning, and then you don't have to rewrite the radical later. So on number 15, I'm going to show you a shortcut. Because these both have radicals, we can put them underneath the same square root. And now they're inside the same square root. The 2 and the 10 are just a fraction. I can simplify them. So what goes into 2 and 10? 2. I'll divide the 2 by 1. Sorry, strike that. I'll divide the 2 by 2 and I'll get 1. I'll divide the 10 by 2 and get 5. Is that okay? Divided them both by 2. So this is the same thing as saying 4 square root 1. We need the square root 1. What is the square root of 1? Just 1, right? So technically we don't even need it. That's the same thing as saying 4 over the square root of 5. So we took just an extra step at the beginning to simplify the fraction before we rationalize. Notice I broke apart the square root again. Now, what would I multiply the top and the bottom by in order to get that square root of 5 to go away? Square root of 5. Personally, I would much rather simplify a fraction than do a factor tree and break up a radical. Does that make sense? It's up to you though. Final answer is what? 4 square root 5 over what? 5. Does it simplify further?
Now. So on your own, let's do 2 more problems. Try problem 8, try problem 10. Make sure you're getting them before we move on. What time are we at here today? Do you know? 10. Okay. In 3 minutes to try at least 1 or 2 of these. Now this step becomes kind of critical because when we start doing trig and trig has a lot of fractions in them, if I ever have a absolute or a square root on the bottom, I have to get rid of it. That's why we've done this step right here. So this one, we don't have to worry about breaking it into pieces and that's totally taken by the mistake. We don't have to worry about that at all. What? Don't say with your work at all or your own money. If you don't speak to you for this, it might not answer. Okay, so on this one, let's multiply the top and bottom right. Square set. And then on bottom, what are we going to put? So it's kind of like the square root of 25. On top, now you check to see if the root is down 30 times 56. So that's 2, 3, and 5. Which means all right, let's head back to our notes really quick, and then we're going to go into your booklet. Head back to page 1, in that little section where it says trigonometry is. The word is very intimidating. It's hard to spell, it's hard to pronounce. It's long and it looks ugly, but trigonometry sounds scary. All trigonometry determine the size of a right triangle?
We're going to set them up into a bunch of ratios. So we'll have fractions and ratios over the entire thing. Now, interesting thing about this is it doesn't matter if your triangle is the size of, I don't know, a coin, obviously coins are round, but if it's that kind of size, or if it's the size of the gymnasium. If the angles are the same, if those triangles are similar, then the ratios will be the same as well. We learned that last unit. If the angles are the same, the sides are proportional, right? So those ratios would be the same. So flip to your notebook that we created. On that very first page, where it says Trig at a glance, you may want to write this word down. SOHCAHTOA. SOHCAHTOA is the word for you to memorize very quickly, and it will tell you what sine, cosine, and tangent mean. There are 6 trig ratios. We will study in depth 3 of them. We will kind of study the other 3 at a glance on day 4. So the three ratios are sine. Now the shorthand for sine is that. It's still pronounced sine. If you call it sin, I'll tell you we're not at church. It's sine, sine. Okay? Cosine, the shorthand is that. Still pronounced cosine though. And tangent. There's a lot of different tangents in math. There's also different tangents in English. This is not any of those. Tan is the shorthand, but we're still going to call it tangent. Now the S in the SOHCAHTOA, the C in the SOHCAHTOA, and the T in the SOHCAHTOA. Oh. There we go. Stand for sine, cosine, and tangent. So the OH, AH, and OA have to do with the sides of the triangle. Now in any triangle, talking right triangle, across from the 90 is always the what? Hypotenuse. Trigonometry is based on an angle, so it's always going to be based on something. We will be using X's a lot, we will be using A, B's, and C's a lot, but I want to introduce you to a Greek symbol. It's like a circle with a line through it. That's the symbol, or the Greek letter theta. You will see that one a lot too. It's TH. Theta, not theta, the G. It's not an F, a TH. Now based on this angle, I have an opposite side. And I have an adjacent side. You can write this, if you want to write this down anywhere, I don't care where you write this down, or you don't have to write it down at all. Now the adjacent side is always in between the 90 and your angle. The hypotenuse is always across from your 90, and then the opposite, you would have to go out through your triangle to get to the opposite side. Now, the O in SOHCAHTOA, or the O in tangent, guess what that stands for? Opposite. The H stands for hypotenuse, and the adjacent is the A. So this is why SOHCAHTOA is so critical. It helps you remember each of the 3 sides. So now let's look at sine in a little bit more detail. If you'll flip to the first page. In the booklet, yes. I don't have any slides of this. Okay, so the sine page. We have this triangle. We always label our angles with capital letters and our sides with lowercase letters. Now what part of the SOHCAHTOA
is the sine. It's the SO part, right? Sine stands for what over what? Opposite over hypotenuse. So the sine stands for opposite over the hypotenuse. All right, so it says sine A. Everything in trig is based off of a certain angle. So it tells me right here which angle I'll be looking at. Based on angle A, if I go through angle A, this is my opposite side, right? Across from the 90 is always your hypotenuse, which means that last one, what are we going to call it? The adjacent side. The adjacent is always between your angle and the 90. Now sine is opposite over hypotenuse. This is my opposite side. This is my hypotenuse. So if I were to make that into a fraction, I'm going to call it A over C. Now A, B's, and C's will eventually be numbers. So it could be like 3 over 5 or 7 over 12 or something. Eventually these will be numbers. What happens then if I change the angle to no longer angle A to angle B? If I change it to angle B, what happens to my side labels? They switch a little bit, right? Is this still the hypotenuse? Yes. But what is this now? It is no longer adjacent. It is now opposite, right? Going through the triangles, now opposite. This is no longer opposite. What is it now? Adjacent. So sine doesn't change. It's still opposite over hypotenuse. It's still opposite over hypotenuse, but in this case, my opposite side is B. My hypotenuse is C. Hey, what's up?
Sounds a little hippie, count a hippie.
Yeah?
Tripping on apple. Anyway, can I switch you for Friday?
Which what?
The luncheon? I can only do B days.
For the food?
Yeah.
Yeah, that's fine. Okay. Sure. You're welcome.
Appreciate it.
Oh. It's funny. There's like, if you walk out of my little window, there's a face print on it, like you can see lips, nose, and like part of a cheek. That's his. Yeah. Oh, okay. Okay. All right, so let's try this in with an example. The math teachers get together on Fridays and somebody brings a treat and then we hang out, whatever. Mostly we just talk about math, but anyway. Okay, so let's make this into an example. So on the other side of your booklet, on this blank side, you have an example, right? Draw this on this triangle with me. So this triangle, instead of ABC, let's make it 3, 4, 5. Okay, so if I see a problem like sine A equals, again, we're just making a fraction or a ratio between the different sides. I know that I'm dealing with angle A because it says sine A. So I'll mark this angle. Now, based on this angle, I need to label O, A, and H. Oh, crap. Which side's O? 3. Which side's A? Good. And then H is this one. So sine is opposite over hypotenuse, which is what over what? Opposite is 3. Hypotenuse is 5. Ta-da! We're done. That's all we have to do. That's it. What happens when I change the angle, though? If I jump over to angle B, is this still my adjacent side? No, it is now my what? Opposite. Is this still my opposite? No, it is now my adjacent. See how those just flop? Does the hypotenuse ever change? No. So if I'm looking for my sine ratio for angle B, sine is still O over H, which in this case would be 4 over 5. And that's all I have to do if I'm looking for the ratio. Now next time we'll use these ratios to figure out how big is angle B. How big is angle A? Like we'll move forward, that's our next step. But for now, I just want you to list the ratio. Notice both of these are less than 1. Will that always be the case? Yes. Why? Because the hypotenuse is always bigger. So this is always the largest side, this is always the largest side, so those two numbers will always be less than 1. All right, we have to cruise. Let's look at cosine now. Yep, that's why you have a booklet. It is a lot to remember, and I know I'm going super fast because class is out in 5 minutes. I have 2 more ratios to tell you. So, now let's deal with cosine. From my SOHCAHTOA, cosine is what over what? It's the part, right? It's adjacent over hypotenuse, right? Now, what is we live kind of in a I can take whatever whenever relationship. I'm sorry. Yep. Okay, I didn't even hesitate. Okay, based on, all right, cosine A equals blank over blank, or like that. Cosine B. What did we say cosine stands for? Adjacent over what? Hypotenuse. So what do you think about cosine? Will that always be less than 1 again? Is the big number always on bottom? You've got small over big, right? Adjacent over hypotenuse. Now we have to figure out which sides are the adjacent and which ones are the hypotenuse, right? Don't pack up, we're not quite done. Angle A. Based on angle A, we're doing this one first. Tells me the angle that I'm going to base everything on right here. What is the opposite? A. What is the adjacent? And what is the hypotenuse? Hypotenuse is always across from the 90. So if cosine is A over H, what do I have here? B over C. Is that okay? A over H, which is B over C in this case. So cosine is adjacent over hypotenuse. Based on this angle, we labeled these sides, right? So adjacent is B, hypotenuse is C, that's my fraction. What happens then if I switch the angle? I realize we're going fast and I realize this is hard. Trust me, you'll have time to learn it. What happens when I switch the angle? This is no longer adjacent, it's now what? Opposite. This is no longer opposite, it is now adjacent. So what's my fraction now? The adjacent is A, hypotenuse is still C, A over C. So let's get an example problem. We'll do the exact example from the previous. So what was this, 3, 4, 5? So for my example, we'll redraw this triangle very fast. All right, if I'm looking at angle A, cosine is A over H, right? Based on angle A, what is your A? Which is your adjacent? Adjacent is 4. How do I know that? Because it's between the angle and the 90. What is your H? 5. So my fraction for the cosine of A is what over what? 4 over 5. But when I switch the angle, this is no longer my adjacent side, it is my opposite. This is no longer opposite, it is adjacent. Hypotenuse stays. So what's my fraction for angle B? 3 over 5. Woo. One more? Do you feel like this is like roller coaster? How are you guys doing? 1, 2, 3, 4, 5. 1 means like, wow. Or, I don't know if anybody can really be 5 right now because we haven't gotten to tangent yet, but 3, 4. I realize we're going fast. Okay, I promise you'll have time to learn it if you're not with me quite yet. Let's do tangent. What's the special word for tangent? What part of the SOHCAHTOA? It's the TOA, right? T stands for what? T stands for tangent. O stands for opposite. A stands for? Okay, so you got that part, right? We got a triangle. Is this C? Which one's A? Top or bottom? Okay,
we need to do tangent of A. Tangent of A equals what over what again? Opposite over adjacent. So in this case, based on angle A, what is my opposite side? This is my opposite side. Which one is my adjacent side? This is my adjacent side. So if tangent is opposite over adjacent, OA, OA's, what over what? Isn't it just A over B? Is that okay? But when I switch my angle, what happens? It's still opposite over adjacent, but this is no longer A, it is now O, across from angle B. This is no longer O, it is now A, so they switch. Opposite over adjacent is what over what? B over A. Notice, those are just flip-flops, right? So will tangent ever be less than 1? Sometimes, but not always. Hold on really quick. I just want to show you something very fast. I promise it will take 20 seconds. Don't crack up really quick. So on one of your problems, it could ask you to find a tangent. Here is how I would do this one. Don't write it down, just watch. I'm asked to find a tangent of something. I mark the angle. This is my opposite. This is my adjacent. That's TOA, right? So my final answer would be 12 over 16. And all I have to do is reduce that. Have a nice day. Sorry that went short. I hate Mondays. Woo!